Hello, class. Our next lesson here is in section 1.5, which will be on the limit of a function. And we kind of saw this already to a degree last time. Only we didn't use that terminology too much, just a slight reference. The limit is to find the tangent to a curve or the velocity of an object. We turn our attention to limits in general, um, and numerical and graphical methods for actually computing them. Mind you, as you could probably guess, the graphical method in forming, like I did here, a table, can unfortunately get a little time consuming, especially if you're trying to do it by hand, which is why I usually don't recommend you doing that by hand. But finding limits numerically. Let us investigate the behavior of f of x is equal to x minus 2 divided by x squared minus 4. Put values of x near 2. And if we try to pop 2 into that, you can see we get 0 divided by 0. No one wants that as an answer. We could see values of f of x for values of x close to 2, but not exactly equal to 2. And again, if we actually use 2, we would get 0 divided by 0, which is a fancy thing called an indeterminate form. But you could see here on the right-hand side, I popped a whole bunch of numbers in, right? And we could see as we approach the value of 2 by going down this table, from 1 down to 1.9999, which in this particular case would be approaching from our left-hand side. So let me actually write that. This is approaching 2 from the left, which is denoted by putting, in this case, like a little negative symbol, kind of almost like an exponent near this 2, just to denote the fact this is coming from the left of our function. You could see that our numbers going from a third, as we start approaching that 1.9999, we're still getting kind of close to a value of 0.25. And if we kept using increasingly closer numbers to 2, we should keep getting that particular value there of 0.25. So in this case, a fourth. So from the left-hand side, that's 0.14. Likewise, if we are going from the right-hand side, going from 3 down towards 2, again, the left-hand side will be denoted by a plus in that position of f of x. This one, as we approach from that right-hand side, we see it goes from that 0.2, getting closer and closer and closer from the right-hand side, also to 0.25. So in this case, 1/4. So we could see from both of these particular instances, the left and the right both approach a value of 0.25, or 1/4, which means overall, this limit as we approach 2 should give us a value of a fourth, based upon what we see, which can look weird, right? Due to the fact that we had an indeterminate form to begin with. There are reasons, though, but for right now, numerically, 1/4. So, in the graphical sense, from the table that we just showed, again, looking from the left or to the right, we would approach that value of 2, which in the case of the graph I have here, has this open circle at that point, which is why the particular function itself doesn't exist. But as we just saw from that last slide, that limit, as we approached 2 from either side, gave us that value of 0.25 or 1/4. Which the only issue with doing this graphically, especially if you try to do it on a computer like I did on this, the open circles don't necessarily always show up nicely unless you like really zoom in. Which is why trying to do it graphically may not necessarily always work out too nicely. But as you can see, we do approach that value of 1/4, even if that open circle didn't display as nice as we would like. So this all gives us this idea of the limit of a function. We can make the values of f of x as close to 0.25 by taking x sufficiently close to 2. What does sufficiently mean? There's no really nice definition for that, but it just means that we take values of x very close to 2. And the notation of that, let's limit as x approaches 2, as I was writing before, of our function x minus 2 divided by x squared minus 4 is equal to 1/4 or 0.25. So that gives us this idea of this limit, and we could define it. So we could actually use it in different situations. Definition of a limit. We can write the limit as x approaches a of f of x is equal to L, or alternatively, f of x, oh, okay, good. I did write it here. F of x approaches L as x approaches a. So when finding the limit of f of x as x approaches a, we never actually considered the point of x being equal to a. I know that definitely sounds a little strange to hear, but that is indeed the case. We never consider when that value of x is equal to a, only when it's defined near a, that neighborhood around the value of a. So, like for example, here on this left-hand most graph, A in this case, we see that this point actually exists here. We have a nice, clearly defined point there, right? This middle one here, I know it's kind of hard to tell nicely, but this one here was actually defined at that point. Nothing weird going on. B here, that point of A is not defined. There's an open circle there, which may be hard to see, but that's exactly what happened. The one here on the right defines it. But the problem with that definition for it is that the point, while there is one, does not agree with the actual function. But no matter which one of these we're actually considering, A, B, or C, in this particular case, all three of these graphs have the same limit, which is why they're here. All three of these. They have the exact same limit, which is that original point, that dark blue point that I drew on graph A. All three of them have that same limit point. So, while we could certainly do it graphically and numerically, let us face it, not necessarily always the easiest to do. So we're going to do this algebraically. Estimate the value of the limit as t approaches 0 of this particular function, the square root of t squared plus 16 minus 4 on the outside, divided by t squared. And we are going to take this expression and we're going to multiply by a value of 1. But not 1 in the traditional sense of 1. I'm going to multiply it by something that helps us, in this case, rationalize the numerator. Let me just write that out just so we know what we're doing. Rationalize numerator. So that, in this case, would be the conjugate of square root of t squared plus 16 plus 4 divided by the square root of t squared plus 16 plus 4. This gives us the other conjugate value here and allows us to multiply and be able to simplify it a bit nicer. So this is the limit as t approaches 0. So multiplying the numerator with its conjugate like that, this simplifies to be that square root of t squared plus 16 times the square root of t squared plus 16. That simplifies to be just t squared plus 16. -4 plus 4 multiplies to make -16. The two middle terms from that cancel out because they're the conjugates, and that's why I chose that as the number to multiply by. Divide by, you can't do anything nice here. T squared times the square root of t squared plus 16 plus 4. But the two 16s in the numerator do cancel. Limit as t approaches 0 of, this should just be t squared divided by t squared times the square root of t squared plus 16 plus 4. But, even after these canceled, we could also cancel out the two t squares here. So this simplifies to be the limit as t approaches 0 is 1 over the square root of t squared plus 16 plus 4 on the outside. And now here, we could stop, because unlike before, at the original portion of this, if we just tried to pop 0 into this particular equation, we would get 0 divided by 0, that indeterminate form, that's not good. But this new form here on the bottom that we just made, if we popped in 0, we no longer get a 0 over 0. So popping in 0 here gives us 1 divided by the square root of 0 squared plus 16 plus 4. So that'll be 1 over 4 plus 4. So 1/8 would be the value of this limit, algebraically. Likewise for this one, guessing the value of the limit as x approaches 0 of the sine of x divided by x. So this, if we try to pop in 0, gives us 0 divided by 0, that fancy sounding indeterminate form. So to actually go through this, I am going to actually hop out of that. I'm going to open ourselves up a graph, and we're going to see what happens here. So this was the sine of x divided by x. And we could see, it's a sine wave and it's, periodic and all that. But we worry about what's happening at 0. I'm going to make this a bit bigger here. And we could see near 0, it's approaching ourselves a value of 1, just based upon the way the graph looks. We could look at it from the left-hand side, and I can move this point closer and closer and closer to 0. And you could see the approximation getting closer and closer and closer and closer and closer to 1. And even though you don't really see the point, the actual hole in the graph nicely, but if I try to hover over this, you could see, well, if it stayed there, that'd be helpful. Undefined due to that 0 over 0. But we could also do this from the right-hand side. The closer and closer and closer we get to 0, we keep approaching that value of 1. Which means, even though this one's not as nice to show algebraically, that this gives us a value specifically of 1. So what we did before were examples of one-sided limits. And I showed that as an example here with a function h called a Heaviside function as a piecewise function that takes a value of 0 if t is less than 0 and 1 if t is greater than or equal to 0. So as t approaches from the left, h of t approaches the value of 0 due to the fact that, well, if it was less than 0, it was 0 anyway. So as t approaches 0 from the right, though, the other thing happens. It gives us a value of 1 due to the fact that, again, it is equal to 1 if we are greater than or equal to 0. So because of that, we have ourselves two different function values here based on the limit. The limit as t approaches 0 from the right gives us h of t of 1. Likewise, the limit as t approaches 0 from the left of h of t is equal to 0. That one being from the left. These don't equal, like the other example we did, right? Because these don't equal, that means this overall limit as t approaches 0 of h of t does not exist. Due to the fact that two one-side limits don't converge. If they converged, we're fine, we're golden, everything's hunky-dory, perfect, and whatnot. If they don't converge, like happened here, it does not exist. Which I just wrote out over here too. The left-hand limit is where the limit as x approaches a, again with that little negative symbol to denote from the left of f of x is equal to L, while the right-hand limit is the limit as x approaches a with that little positive symbol to denote that right-hand side of f of x is equal to L. And we could see that happening actually on both of these as we're approaching left and right on both of these particular pictures. And so because of that, we can write the overall limit as x approaches a if f of x is equal to L, if and only if the left hand and the right hand limits both converge to that same point. If it does not, then a limit does not exist. We can also do these based upon pictures, like the ones I have here, which thankfully clearly show where we have open circles. The limit x approaches -2 from the left. Oh, we could see that going on here. So approaching from the left. It's approaching us as a value of 3. If we're approaching from the right, we do here, we get a value of 1. Those don't converge, so this one does not exist. With the overall limit as we approach -2. If we approach +2 from the left, we get ourselves a value of 2. If we approach +2 from the right, this also gives us a value of 2. Both of those equal, so this gives us a value of 2. Despite the fact that we have this extra point down here, but we could ignore that as that's not needed for that. So, again, these limits don't exist when the left and right hand limits are not equal. This also happens when it oscillates without bound, and a couple of other instances also, but we would see those as we get to them. For example, number 4 here, I want to investigate the limit as x approaches 0 of the sine of pi over f. Actually, let me reopen that graph. I'm going to edit this. This should be the sine of pi over x. There we go. We could see that oscillation happening here, right? So badly, as a matter of fact, that as you can see, it's practically like squishing in each other, the middle there, as we approach the value of 0. But you can see a crap ton of points here. Even if I tried to zoom in on this, it doesn't really make any clearer. As you can see, it oscillates way too much. Where no matter if we approach from the left or the right, we are not getting the same value. So because of that, since it's oscillating that much, to actually answer this would be a does not exist. Due to the oscillation. This fifth one, we wanted to find the limit as x approaches 0, 1 over x squared. If this one exists. And in this one, something else is going to happen. 1 over x squared. And let me zoom out so we can see what's happening here. As we approach that 0 here, we could see the left and the right hand side. They both increase without bound, right? I attempted to get closer and closer to 0. It's still getting off the page, so I can't really show too much. But, it keeps going up on the left and the right. So both of these, on the left and the right, both of these for the limit as we approach 0 of 1 over x squared. Since they both increase without bound, this should be equals to infinity. It keeps increasing, and more increasing. So infinite limits, which is what that's an example of, is a f be a function defined on both sides of a, except possibly at a itself. Then the limit of as x approaches a if f of x is equal to infinity means that the values of f of x can be made arbitrarily large by taking x sufficiently close to a, but not equal to a, which means f of x approaches infinity as x approaches a as well, which we could see is what's happening in this graph, right? As we move here to the left and to the right, we're increasing without bound, which is why this limit approaches infinity. Likewise, that was positive infinity that we just saw. Same thing applies for negative infinity. So if we have a function be defined on both sides of a, except possibly at a itself, the limit as x approaches a if f of x is equal to negative infinity means the values of f of x can be made arbitrarily large, negatively, by taking x sufficiently close to a, but not necessarily equal to a. And we can write this as f of x approaches negative infinity as x approaches a as well. So keeps decreasing without bound. So because of that, negative infinity. So I gave examples here of infinite limits with the one-sided limit portions involving this. So the limit as x approaches a from the left of f of x is equal to infinity is an a for b. It's also equal to infinity, but on the right-hand side. The left-hand side on C going to negative infinity, just like with the right-hand side in D, which is what these pictures here try to show. Just to give other ideas as to what that could look like. So finding the limit as x approaches 1 of x squared minus 2x plus 1 divided by x minus 1 cubed. If we popped 1 in, we get 0 divided by 0, that fancy indeterminate form, which is not good. We could factor this numerator. X squared minus 2x plus 1 factors to be x minus 1 squared over x minus 1 cubed, which we can reduce. This makes the limit as x approaches 1 of 1 divided by x minus 1. The problem here, though, is if we pop 1 into here, we get 1 divided by 0, which is definitely not good. So because of that, this one does not exist. Due to that nature. That's algebraically. We can also see it graphically if we pop this into a graph, which let me do that very quickly. And I'll just pop in actually the original without me simplifying it first, just so we can see that this is indeed the case. Just by popping all of this in. Okay, good. All right, so we could see as we approach ourselves that value of 1. From the left, we are decreasing without bound, as we can see. That keeps on decreasing. Likewise, if we move from the right and increase without bound, you can see, not too far, that it keeps increasing without bound. So the left-hand side decreases without bound. The right-hand side increases without bound, which I could write out just so we could have that physically out here. I'm not going to rewrite the function both times though. But as we're approaching 1 from the left, this function decreases without bound towards negative infinity. And if we approach from the right, this function increases without bound to infinity. So even though we have those infinity symbols here, they're not the same exact infinity, which is why this still does not exist. Vertical asymptotes. So for this, vertical line x is equal to a is a vertical asymptote of the curve y is equal to f of x if at least one of these statements holds, where we have left and right hand limits and overall limits being equal to positive infinity or negative infinity. Then we have ourselves a vertical asymptote. I know there's a lot there, by the way, but they all basically read that same function. We want to find the vertical asymptotes, though, for this tangent of x function from trig. Here we could rewrite this tangent of x as the sine of x over cosine of x, just based upon its definition. So in order for us to actually have a vertical asymptote, that could be when we have our denominator here equal to 0. So in our case, the cosine of x being equal to 0 would be a potential location for this. So for this cosine of x is going to approach ourselves a value of 0 from the right. As all values of x approach a value of pi halves from the left. Why is that the case? That's because as we approach pi halves, we do get a value of 0 for cosine. Likewise, the cosine of x approaches 0 from the right as x approaches pi halves now from the left. So due to that unit circle, which I could quickly just draw on here just so we can see that, we approach 0 as we have the values of x approaching 0 here on the left or the right. We're going to be approaching ourselves a value of 0. And because of this, we also know that the sine of x is going to be positive, close to a value of 1, as we get closer and closer and closer to that pi halves, but it's still greater than 0. As x approaches pi halves from both the left and the right. I won't put both in there just because it's kind of confusing if I wrote all of it all together. So because of all this means the limit as x approaches pi halves from the left of the tangent of x is equal to infinity, and the limit as x approaches pi halves from the right of the tangent of x is going to be equal to infinity. Negative infinity in this case. So all that combined, let's write this down here, is there are asymptotes, vertical asymptotes, are going to be when x is equal to pi halves, then 3 pi halves, 5 pi halves. So we're going to add to that n times pi, as there's an infinite number of them. So let me know if any of you have any questions or concerns. Thank you.